Thanks very much for inviting me to talk here. And actually, it's a great honor to speak in this special session of anniversary. Actually, officially, since it's the last talk of this conference, I have proposed that we thank all the organizers and local staff for running this wonderful workshop. I will be talking about some mathematical structures for Topos string and BCOV theory in particular that I've been searching, exploring for the last few years, and in particular the so-called semi-infinite Hodge structures. And I'll also describe some recent development. So, first, this semi-infinite Hodge structure originated from Kyuji Saito's theory of higher residues in primitive form in his study of a period map for isolated singularities. And actually later this is generalized and systematically developed in Calabi-Yau geometry by Barnikov and Kantsevich, so giving this official name, semi-infinite Hodge structure. And in this talk, I'd like to explain the role of the semi-infinite Hodge structure from two perspectives. I mean, the first one is about this B-twisted topological stream field theory and BCOV theory. Second one is about the Seiberg-Witten geometry realized by singularities, and of course, these two stuff are not disconnected. So, here's a rough outline. Let me start with the singularity stuff. I'd like to motivate this semi-infinite Hodge structure from Kyuji Saito's original version in singularity. So suppose let F to be the germ of an isolated singularity, so say F of n+1 variables. Now, the natural thing we can consider, for example, we can consider the quotient, omega F, which is the germ of holomorphic n+1 form, quotient by df wedge n forms. And if you choose with the choice of holomorphic volume form, for example, like that, and then we can identify the space with the space of Jacobian algebra of the singularity. And also there's a classical structure that there's a non-degenerate pairing on this omega F given by this residual pairing. And that's a very classical structure. Now, what's more striking is the following. Like this omega F is the leading part of so-called Briscoe lattice, which is defined as follows. So you look at the holomorphic top form divided by df wedge exact form. So this is a little bit different from the original previous construction here. Now on this Briscoe lattice, there is a well-defined operator. Let us denote it by a formal variable t. And so t acts on this space as follows. Suppose I have an element here represented by a top form n+1 form. Then locally, I can always find an n form such that alpha equals d beta. Then this operation, t operation, applies to alpha begets minus df wedge beta. So symbolically, I mean, you can remember c by this operation, which sends alpha to first apply d inverse and wedge d alpha. And because of this relation, you can show this actually is a well-defined operation on the Briscoe lattice. Now, with this structure, we have a notion of so-called descendant forms. This descendant is motivated from this notion in commutation theory. I'll explain more about it. And so suppose I got an element of the Briscoe lattice, for example, and a non-negative integer k. So we can define k's descendant form by applying this operator k times. So it's still elements here. Now, this descendant forms actually give a natural semi-infinite filtration. It goes to the left forever. Now, if you look, it's actually sometimes more convenient to work with the formal completion of this Briscoe lattice with respect to this filtration or this kind of t-adic topology. And it becomes a very familiar object. So it's like forms with a formal variable t added divided by such a differential. So it's a deformation of df. It's like representing this twisted around. So now, moreover, like on this Briscoe lattice, Kyuji Saito defines a bilinear higher residual pairing. So it has many terms. It's valued in this basically this formal power series ring. And somehow the leading term coincides with the residue parent. For example, we can identify this omega f that previously defined to be the quotient of this lattice by T. And then you pick up the leading term on the right-hand side. That's precisely the higher residue parent. But now you look at higher orders of T, the value actually, that's why it's called a higher residue. I mean, you get towers of values. And for convenience, we can further extend this higher residue parent to the following space. I mean, you look at this formal Lorentz series, basically. This kind of, it's also called Gauss-Monier system, or this kind of twisted around. But adding into this T inverse, so you work with the formal Lorentz series, and write this higher residue parent as the parent value in this series. So this is the basic structure. Now, here we got enough motivation to give a formal definition of this semi-infinite Hodge structure. So I'll just say a few words. Like a semi-infinite Hodge structure of weight n consists of the following data, where H is a finite dimensional vector space over the ring of formal Lorentz series. So we can think about this H as a vector bundle on the formal disk. Now E is actually a lattice, so we can think about this one as an extension of this bundle to the puncture. Now lambda is a meromorphic connection on the formal disk, so with a particular order. And finally, this K, which represents this higher residue parent, somehow compatible with the connection in some sense, and which is just linear and symmetric in some sense. And in particular, the leading term of this one gives rise to a non-degenerate parent, just like a residue parent. So, for example, this Gauss-Monier system, this kind of Briscoe lattice, this actually I didn't discuss, but this is a Gauss-Monier connection, and the higher residue parent forms a weight n semi-infinite Hodge structure. And actually, if you deform the singularity, this structure varies along this deformation with very good properties. But I won't discuss this variation. And that's the basic structure for this semi-infinite Hodge structure. Now, so given the element of this Briscoe lattice, we can consider this oscillating integral, I mean, over these lattice symbols. Under Laplace transform, and this is related to a period map of this form, now it's an M form, over the Vannish cycle. I'll just make a comment that I'll come back to later. See, in Seiberg-Witten curve geometry, like we have two form omega. Let's say omega equals like d lambda. So lambda is a Seiberg-Witten differential. And somehow like the Seiberg-Witten period map is related to the period map of the first descendant of omega in the following sense. For example, if you look at an integral of lambda, the Seiberg-Witten differential, and we can write this lambda as something like that, d inverse wedge df over f. And then, by our definition, this is the first descendant of the two forms, now over df. And as we will see, actually, this observation allows us to obtain like a Seiberg-Witten differential arising from like higher dimensional geometry, and in particular, threefold vibrations. And by choosing different component descendants of an appropriate volume form. And okay, that's the semi-infinite Hodge structure. Then, with respect to this structure, there's a surprising outcome. So it's a so-called primitive form. So let me briefly explain this. So let M to be the universal deformation space of the singularity, and represented by universal unfolding. So here lambda is the parameter for the deformation. Now using this semi-infinite Hodge structure, Qt constructed a special family of holomorphic volume forms that varies along this deformation, which it calls the primitive form. So the point is that this primitive form actually determines a set of flat coordinates, very distinguished coordinates on this moduli space, such that if you study this the period map of this oscillating integral of this primitive form is satisfied the following like quantum differential equation. And in particular, this A alpha beta gamma is nowadays the core coupling of 2D lambda Ginsburg B models. Now, on Calabi-Yau geometries, the analog of primitive form is called semi-infinite period map. And actually, in the context of Gormiti theory, this is a related give and tell J function. Okay. That's my brief review of the semi-infinite Hodge structure. Now I'd like to discuss this structure in topological string, in particular BCOV theory. So for simplicity, let me discuss the setup for compact Calabi-Yau, although it also applies to non-compact case. Now, around 1994, like purchasing the Secoria Buri-Baffa, they proposed that this kind of bit-twisted topological string field theory, closed, on Calabi-Yau threefold can be described by the notion of like Kodawa-Spencer gravity. And this describes the deformation of Richard-Flip metrics in terms of complex structures. So it's like Calabi-Contractor Yau theorem. Now, a couple of years before, like with Kevin Costello, we find actually an extension of this Kodawa-Spencer gravity in the sense of Seiberg. I'll explain this more later. And it's formulated for upstream Calabi-Yau, upstream dimensions. And we just call this one BCOV theory. And this formulation is nice that it can couple with the Witten's open string field theory. Like in this case, it's holomorphic string assignments in terms of cyclic version of conservative formality. Again, I say more words about this coupling. So to explain this BCOV theory, let me just start with the familiar notion of the periods on Calabi-Yau threefold and its relation to mirror symmetry. So it roughly goes as follows. Let's focus on a compact Calabi-Yau, let's say X naught. Let's consider the modular space of a pair. So it's two information. So it parameterizes X, which is a deformation of X naught, and omega X, which is a choice of holomorphic volume form on this X. So it's a pair. And let's look at this following period map, which is the map from this modular space to H upper 3. So this is locally defined in this case. That it sends the pair to the holomorphic volume form, so which also represents the Ram class, and which locally is identified with respect to the Gauss-Menin connection. Now, here's the observation that, first of all, H3 is a symplectic space. So the symplectic pairing is given by this integration. And now this local toriality is seen, and this variation tells you that this P embeds this modular space into a Lagrangian submanifold of this symplectic space. Now we have some standard trick. For example, if you choose a splitting of the Hodge filtration, you can write this H3 as a cotangent bundle of something, of base, let's say F2, which basically collects this data. Now, from symplectic geometry, we know that any kind of Lagrangian submanifold of cotangent bundle is a graph of closed form. So we can write down the corresponding generating function, which is F0 here, and this is precisely the pre-potential. So in practice, we choose the splitting from the large complex limit using the monodromy splitting, and you compute this one, you find the mirror to generating functions of genus 0 Gromitian events. So that's the familiar story. Now, this suggests that we should study somehow the deformation of the pair. So this pair deformation can be specified by two data. One is mu and one is rho. So mu is a 0-1 form valued in this 1-0 vector field, and the rho is a smooth function. So basically, this mu specifies a new complex structure, so it satisfies this Maury-Cardan equation. Now, rho specifies a new Calabi-Yau volume form. For example, if you have this complex structure, this one with this expression defines a new somehow N0 form, but you require this one to be holomorphic, so you have to correct this one by an additional function. That's the rho. And somehow you can combine these two equations into a single equation by writing this mu tilde as mu plus t rho, where t is the formal variable, and q is the following differential. So t bar plus t del, where del is the divergence operator with respect to the Calabi-Yau volume form. So this is very nice. And actually, this motivates our following definition for the field content, our generalized BCOV theory in the following sense. So we define the fields of BCOV theory on a Calabi-Yau by the following data. So it's the polyvector fields with the formal variable t. And so here it's given by all these kind of polyvectors, smooth polyvectors. And E has a differential q. The same differential is d bar plus t del. And del, again, is the divergence operator. And also, this one has a shorter near-His bracket. So in particular, if you look at associated Morikawa equations, this somehow describes the extended deformation of the Calabi-Yau structure. And for example, this is used by Barnikov-Kancevich to obtain Frobenius manifold structure for compact Calabi-Yau. Now, here's the key observation, like this space, we can define the analog of higher residual pairing by the following. So you have ft alpha, gt beta, you define a sesquilinear pairing, so you pick up these, and now for the polyvectors, you can integrate against the holomorphic volume form. And actually, you can show that if you in the Landau-Gisbert case, you deform this Q by twisting with the Landau-Gisbert superpotential and pass to cohomology. This is precisely the QT Saito's higher residual pairing. Now, here's the problem. So we described the fields of the generalized BCOV theory. Now let me describe the equation motion. I just mentioned this equation motion for this Morikawa equation describe the deformation of Calabi-Yau structure. This can be viewed as a resolution of BCOV's original Cauchy-Spencer gravity, whose fields are given by this non-local stuff, like this divergence-free polyvector fields. So it can be viewed as a resolution of this condition by this variable t. Now, somehow to generalize this Cauchy-Spencer gravity, we need to find an action functional whose variation gives the above equation. So we tried for a while. I mean, it turns out, unfortunately, such action doesn't seem to exist. I mean, to me. After a while, like the solution is the following. Like surprisingly, and we found a nonlinear L infinity transformation of this equation. And after this equation, we can write down a local interaction whose variation gives the desired transformed equation. I'm going to call this one BCOV interaction. So I will explain basically how this transformation is defined. So this is defined as follows. So first, we need to explore more about this infinite Hodge structure. So this nonlinear transformation that allows us to write down this local interaction is given by the Coulomb period map. So let us define S of x by these polyvector fields. Now we add into all of this formal Lorentz polynomial series. Now this one is equipped with a non-degenerate school symmetric pairing. So this plays a role like a sympathetic structure on the loop space. Now let's consider the following period map. And this map actually, strictly speaking, is only defined as a formal map between two functors on this itinerary, but let me ignore this technical issue. So the map from the fields to S of x is defined as follows. So start from a mu, you map to this guy. E to the mu over t minus y times t. So this one is nothing but representing the deformation of the volume form. This is a period. And this minus 1 or minus t basically is about this dilatant shift. So let's represent this map as something like that. Now, so you can interpret this map as basically the period map for Calabi-Yau geometry at the Coulomb level. Now, you can show that actually this period map embeds these fields as a formal Lagrangian submanifold of S of x, and which is also tangent to the linear vector field generated by this infinitesimal transformation Q. So this Q plays a role of like an infinitesimal gauge transformation. So this one is a gauging invariant basically. Now we have the same story. Now we have a Lagrangian submanifold inside a sympathetic space. Now we can use this isotropic splitting of S of x. This is our fields, and we add into the negative part. So we can formally write this one as a cotangent space of our fields. And this formal Lagrangian, you can write down the corresponding generative function for this formal Lagrangian. So let's call this one I0. Now, if you compute this I0, you find something very surprising. This function actually is a local functional, and is given by the following expression. So this bracket E to mu, like you have to do a power 6 expansion for this one. So this interaction contains like infinite many terms. So for terms with like an input, for example, this bracket means like pick k1 mu1 essential. You pick up the following coefficient, and then you take the wedge of the polyvectors, vectors, and then you integrate. And you observe that this constant is the intersection number on this moduli space of rational curves. So somehow this reflects the fact that this topological B model is localized around the constant map. Now, moreover, like this space, it turns out that this one has a -1 shifted degenerate Poisson structure. This one is degenerate, is a fact, reflecting the fact that in the original Coulomb-Spencer gravity, this free part is somehow like ill-defined, so it's only Poisson, not symplectic. And then this Poisson structure induces a degenerate B-way bracket, but this one is well defined. And then this classical action functional satisfies the following classical B-way mass equation. So we are pretty much in the standard setup for like studying a gauge theory in the BIST B-way formalism. So note that actually this term, like starting from qubit interaction, so when n equals 3, and that qubit interaction is precisely the interaction of Coulomb-Spencer gravity. So this is like an extension of this Coulomb-Spencer gravity along this descendant parameter. And also, actually, Andrew Offset has a similar construction a long time ago for somehow a finite dimensional model of this guy in some algebraic setup. Now, let me explain this nonlinear transformation, which is given as follows. So once we have a solution of classical mass equation, now we have a standard version that this vector field on the space of fields squares 0 and defines a cohomological vector field. And the zero locus of this cohomological vector field, this collects all of this like equation motion and gauge symmetry and so on. Now, in mathematics, I mean, this defines a so-called local Euclidean structure on the space. Now, this nonlinear transformation on the fields sends mu to this expression. The inside is the Piri map. And now we take the non-negative part of this Piri map. So here's the picture for this map. So originally you have the fields, you map to this sympathetic space by this Piri map, and you truncate. Basically, you project down to this field. And I can show that, so this is a highly nonlinear map. If you write it down, it's complicated. But I can show that actually this sends the solution of the original Mori-Kanai equation into the zero locus of this cohomological vector field. So we are pretty much in the standard formalism now. So that's how this transformation is constructed. Now, start with a solution of this classical mass equation. It's a standard to see how to quantize it. So there's a standard quantization in the B-way formalism. So it amounts to find quantum corrected functional by correcting this one by one loop to two loop essential and solving the quantum mass equation. So here delta is the B-way operator associated to the shifted Poisson structure. But now we're working with infinite dimensional versions like quantum field theory, and this delta actually is yield defined mathematically. So this suffers from the U-way divergence. But again, we can make sense of this one using Castello's homotopic renormalization theory. Basically, the idea is the following: like original point is yield defined, but you want to make a regularized B-way operator in such a way that it doesn't lose any information about the original B-way structure. So it goes to different regularizations, and remember this regularization is up to homotopy. So then you can define your theory original point here by studying all the families around. So that's the basic idea. So anyway, you can make sense of this equation. Now, after solving this equation, you obtain a generating function of zero mode by collecting the G-loop Feynman diagrams. So this zero mode here is given by this cohomology of these fields. Now, if you choose a splitting of the Hodge structure, this cohomology can be identified with the cohomology of these polyvectors with the formal variable t. So this identification is not canonical, requires a choice. And actually, now this basically defines a higher genus B model invariance in our generalized BCOV theory. And this is conjectured to be mirrored to the higher genus commuting invariance with descendants. And also, as I said, like this one depends on the choice of splitting, and such a dependence is precisely the holomorphic normal equation. And the geometric interpretation of quantum B-wave mass equation is the following. Like, actually, you can formulate this, the stuff that this one actually defines a Q-closed element of the Fock representation of the wire algebra that quantize the DG symplectic space. So you have the symplectic space, you have a differential compatible with this omega. So that's the geometric interpretation of this quantization. So, so here's one example. So if you can apply this one to equity curve. So Calabi-Yau threefold case, probably you don't need descendants to compute the basic partition function, but on the other dimensions, the descendant become essential. On the curve case, you can show that there's a canonical solution of the homotopic quantum B-wave mass equation for this BCOV theory. So I actually can compute the generating function with respect to the monodromy splitting around this large complex limit, and can actually compute it and find that it coincides with the full descendant Gromity invariance of the mirror elliptic curve as computed by Okenkopf, Pandora, Panda. So this theorem basically generates a classical result by digraph for his cubic interaction, and actually fully established the higher genus mirror symmetrical elliptic curve. So this is one example. Now, I want to discuss some applications. So here is the first application about explanation of the integrable hierarchy. So we always often find that if you count curves on Calabi-Yau geometry, you look at its generating functions, you always find somehow like this KdV type integrable hierarchy. And we want to understand this from, well, we have different ways to understand this one, but I would like to propose explanation in the B model in terms of the quantum mass equation of BCOV theory. And so roughly speaking, this is as follows. Like, suppose I work with the Calabi-Yau geometry. Now I iterate B model by adding one dimension higher. So we get let's consider X cross C. So this is again Calabi-Yau. Now the trick is the following. Like so this is again Calabi-Yau. You can still look at the B model or this kind of BCOV theory on the product space. And now you integrate all the modes on X. Integrate it out, you get effective 2D Cairo theory on this complex plane. And the slogan is that, so by abstract nonsense, you know, the quantum mass equation upstairs push forward to a quantum mass equation downstairs. If you analyze the corresponding B-wave mass equation, the slogan is that this B-wave mass equation precisely captures the integrable hierarchy associated to X. So precisely, the reason I would expect something like this is the following. Like, when you do this push forward, you can find an interdimensional abelian Lie algebra, which is parameterized by cohomology of X with the formal variable T, and valued in this translations along this complex plane. And this interdimensional abelian Lie algebra acts as a symmetry of the effective theory downstairs. And so you would expect find that the nodal currents give commuting operators harmonious. We don't have explored deep enough for this stuff yet, but I can show that at genus 0, the classical level, such commuting currents precisely lead to the Brownian expressionless integrable hierarchy associated to a Frobenius manifold. So this looks very promising. That's one thing about this explanation. So I'm not sure how this is related to actually this integrable hierarchy for the mirror of local Calabi-Yau case in the work of like Mina digraph Marina Clem-Waffa. And I'd like to, probably I would try to see more about it later. So that's about integrable hierarchy. Also, I would like to make some comments, remark on this B model open closed string field theory. So the BCOV theory, somehow this closed string field theory can be coupled with Witten's holomorphic chain-Simon theory to give this kind of open closed string field theory, the B model. And somehow it's required to satisfy Dvořák's open closed B-wave mass equation, and this gives a very strong constraint. So actually, the interaction actually turns out to be the following. So now we can find the couplings for mu is the element of this BCOV field, so it's closed string field. and A is the connection for the open string field. And the coupling is realized by the following. So the coupling constant is given by integration over the configured space of the disk. And so here is a configured space with, let's say, m points in the interior, m points on the boundary. And this Lagrangian density is of the form of Kontsevich graph formula of the deformation quantization. It's basically a cyclic version of this. And so you have many, many terms. And in particular, this Kontsevich formality theorem is essentially equivalent to Dirac-Bach's mass equation for open-closed string field theory. So at the classical level, the explanation of this classical B-wave mass equation has a bunch of terms like Q, and also B-wave bracket in the open string sector, and the B-wave bracket in the closed string sector. And here is the example of the first order coupling, which is nothing but the classical Hochschild-Rosenbach map. They deform your holomorph tensor by this term. Now this is about this this open-closed string field theory. Now I would like to talk about the second part. It's about the singularity and Seiberg-Witten geometry. So we're interested in this 4D equals 2 superconformal field theory. And Seiberg-Witten discovered that for many theories, this low energy effective theory on the Coulomb branch can be described by a Seiberg-Witten curve fibered over the moduli space. So here is a family of curves, and lambdas some parameters, for example, including like coupling constants, math parameters, and expected values for Coulomb branch operators. And the periodic integral of appropriate waveform over this Riemann surface determine basically the low energy for photon coupling. So that's the basic structure. And now we would like to understand the appearance of this kind of superconformal field theory arising from singularity. And I learned this construction from my collaborator, Dan Xie. So it roughly goes as follows. And we consider a type 2B string theory on the following background. So here, X is a threefold weighted homogeneous isolated singularity. So somehow, in some limit, it's argued to define the 4D equals 2 superconformal field theory in the work of Shapiro-Weffer around 1999. And so recently, systematic studied by the work of Xi and Yao. And the Seiberg-Witten differential in this Seiberg-Witten solution in this case is associated to a threefold vibration. So you have four variables here. It's hypersurface, and which may or may not be reduced to the curve geometry. Somehow this suggests that the more general Seiberg-Witten solution could be threefold vibrations rather than curves. But anyhow, our goal here is to figure out the corresponding Seiberg-Witten differential. Now, let me collect some basic data. So we're looking for this threefold singularity and consider isolated weight homogeneous threefold singularity. So here, you have four variables. Qi is a weight. So in such a way that the polynomial has weight 1. So Qi is the weight of the variable. And this rational number, as I mentioned, 1 minus 2Qi, is the central charge of the 2D Lambda-Gibbs model with a superpotential F. Now, there are some conditions to define a 4D superconformal field theory given by this condition. So actually, it's equivalent to the central charge is less than 2 in this dimension. But this is the basic data. Now, the Coulomb branch of this associated equals 2 superconformal field theory is described by the local moduli of the mean universal deformation of the singularity. So we deform this polynomial by a bunch of terms. So here, phi alpha is the basis of this Jacobian algebra. And so lambdas are these parameters for the deformation. Now, you can organize these parameters into different categories. So if you normalize the weight of the parameter by this factor, and here Q alpha is the homogeneous weight of this deformation. So it has a coupling constant. In the middle, you have these mass parameters and also kind of the expectation values for these Coulomb branch operators. And it's very nice that it's symmetric, perfectly paired, as expected. Now I can consider a family of holomorphic volume forms, let's call this one C at this moment. And then we consider the period map over these vanishing cycles. And you can view this one as a map to H upper 3. Now, for simplicity, let's consider the case with no mass parameters. So H3 is a natural symplectic structure deduced dually from the intersection pairing. And this allows choice of an electromagnetic charge lattice from H lower 3, for example. Now, here's the problem. We know this low energy effective theory of Coulomb branch is described by Seiberg-Witten geometry. Now the question is like, what is the Seiberg-Witten differential associated to these singularities? Here's a naive guess. My guess like this Seiberg-Witten differential is a family of 3 forms, like the trivial 4 form over this TF. And actually, then no matter, so if this is correct, then this n equals 2 prepotential comes from this corresponding period map. And this is indeed true in the case of AD singularities. So it's the same as saying that its central charge is less than 1. But actually, if you go beyond AD singularities, this no longer holds. So here's the proposal, our solution. It's a joint work with Danxi and Yao early this year. So for free-fall singularities, we find that actually, if you start with QG Saito's primitive form, this is a very special family of 4 form, and then look at this 3 form, this could be the good candidate for this Seiberg-Witten differential. Well, the main support for this claim is the following: like, somehow we need to figure out, this relation. The main connection between this kind of primitive form and this Seiberg-Witten differential is the following strong integrability condition for the existence of n equals 2 prepotential arising from Seiberg-Witten period map. And then the verification of this such integrability condition requires a knowledge between the intersection pairing for vanishing homology and the period map. And the primitive form precisely provides such a relationship as shown by QG Saito. So, I would like to give some comments about to compare with different dimensions. So the curved case and free-fall case. So this result also generalized to curved geometry. That you have a Seiberg-Witten, you have a primitive form for the family, then the first descendant of the primitive form over DF should be the Seiberg-Witten differential. And we have seen this already in the beginning. And so you see like the Seiberg-Witten differential for threefold geometry picks up the primitive form. Well, for this curved geometry, it picks up this first descendant, somehow by the reason of shift Hodge theory arising from the shift of the dimension. And actually, this is also a 5D hypersurface singularity example, and the analog discussion implies that the Seiberg-Witten differential is given by the -1 descendant of the primitive form over here. Now, I would like to give some examples of the primitive form, and in particular, the Seiberg-Witten differential. The first class of examples is about ADE type, where the central charge is less than 1, for example, of this polynomial, s1 squared, s2 squared, s3, x3 to the k, and x4 to the n, with this condition satisfied. And so this is a square, so this example can be reduced to a curved geometry. And this is a primitive form in this case, it's trivial, so it doesn't depend on the deformation parameter. And the threefold Seiberg-Witten differential is precisely the trivial form over this df. Now, the story started to get complicated and non-trivial if you go beyond ADE. The first, so I do an example from this simple elliptic singularity where the central charge is equals 1. So I pick up this example, x1 cubed, x2 cubed, x3 cubed, and x4 squared. And the universal deformation of this singularity has 8 dimensions. And the last one is special. It doesn't rescale, so it's a marginal parameter. And the primitive form of this example is non-trivial, and also actually it's not unique. And it's a rescaling of the trivial volume form by a function which only depends on the marginal parameter, And this P of lambda h is the period on the curve defined by this qubit equation. So, so this one started to get corrected. Now, things get more complicated. I mean, if you go to, essentially try to become bigger. So for general singularities, actually, there is a highly non-trivial mixing between this relevant and irrelevant deformations. And we don't know a closed formula for primitive form. And so here's one example, like x1 squared, x2 squared, x3 cubed, and 7. So this is a type E12 of one of the unimodular exceptional singularity. And the universal deformation is the following. It has 12 deformations. And the last one scales negatively, so it's an irrelevant deformation. The previous lambda 1 to lambda 11 are relevant deformations. And now, as I explained, like we don't have a closed formula in general yet to write down the primitive form. But on the other hand, we have a recursive formula. It's a perturbation formula to compute the primitive form up to any order we want. So this is developed with Zhang Li and Q Saito a couple of years ago. So if you apply this formula to the example, this E12, and you can make some computer code, it computes up to order 10 of the following form. So you see like this lambda 12 appears everywhere, and it's coupled with other stuff in a highly non-trivial way, and also different polynomials appear. And I don't have a good way to understand all of these numbers and whether a better formulation of this formula. And somehow you see that in this example, the Seiberg-Witten differential is not given by a rescaling of the trivial form. And also a bunch of complicated couplings between relevant and the irrelevant deformations appear in this way. So I hope that exploring geometry of Seiberg-Witten can help to get deeper insight about the structure of the primitive form, and all the other way around, this primitive form probably give a better understanding of this Seiberg-Witten geometry in this situation. Thank you very much for your attention.